Imagine looking up at the night sky and wondering, what secrets does the universe hold? Among the countless stars and galaxies lies something so mysterious, so powerful, that it defies our understanding: black holes. These cosmic enigmas are the ultimate playground for science, challenging the very limits of physics. How do they form? What are their secrets? And why should we care? Let's begin this fascinating journey to uncover the wonders of black holes. Imagine a place in space where the rules of physics collapse and time itself seems to stop. Welcome to the world of black holes. These cosmic enigmas are more than just stellar oddities, they are key to understanding the universe. But what exactly are black holes, how do they form, and what makes them so extraordinary? In this video, we'll explore the science behind these cosmic giants, and why they continue to captivate scientists and dreamers alike. A black hole is one of the most mysterious and fascinating objects in the universe. At its most basic level, a black hole is a region in space where gravity is so strong that nothing, not even light, can escape. This gravitational powerhouse is created by the collapse of massive stars, compressing matter into an incredibly small volume. But what does this mean in practice? At the very heart of a black hole lies the singularity, a point of infinite density where the known laws of physics no longer apply. Surrounding the singularity is the event horizon, the point of no return. Once anything crosses this invisible boundary, it is inevitably pulled into the singularity. Black holes aren't just voids in space. They are dynamic and powerful entities that shape the very structure of their surroundings. For example, they pull in nearby matter and form accretion disks, rings of superheated gas and dust that swirl around the black hole, emitting intense radiation as they spiral inward. This behavior makes black holes some of the most energetic phenomena in the universe. Black holes also bend space and time. To visualize this, imagine space-time as a two-dimensional fabric. When you place a massive object on it, the fabric dips. A black hole is like a bottomless pit in this fabric. This warping of space-time is so extreme that it creates phenomena such as gravitational lensing, where light bends around the black hole, allowing us to see multiple images of the same star. Furthermore, black holes exhibit immense tidal forces. These forces stretch and compress objects that get too close in a process known as spaghettification. Imagine an astronaut venturing too close to a black hole, feeling their body elongate into a thin strand. This bizarre yet fascinating phenomenon illustrates the power of a black hole's gravity. Despite their ominous reputation as cosmic vacuum cleaners, black holes actually play a crucial role in the universe. They influence the formation of stars and galaxies, and their immense gravitational pull helps hold galaxies together. Studying black holes not only reveals their fascinating properties but also offers clues to the universe's most fundamental mysteries. Most black holes form from dying stars. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The outer layers of the star collapse inward, creating an intense explosion known as a supernova. This explosion ejects the outer material of the star into space, leaving behind a core so dense and compact that it becomes a black hole. This process is as spectacular as it is destructive and is one of the primary ways stellar mass black holes are born. But not all black holes form this way. Some arise from more extreme cosmic events. For instance, when two neutron stars, extremely dense remnants of collapsed stars, collide, they release a torrent of gravitational waves and may form a black hole. This process, known as a kilonova, is both rare and awe-inspiring, producing not only black holes but also some of the universe's heaviest elements like gold and platinum. Then there are the colossal supermassive black holes found at the centers of most galaxies. These giants, millions to billions of times the mass of our sun, likely formed over billions of years. Scientists believe they grow by consuming vast amounts of gas, dust, and stars, as well as merging with other black holes. Another fascinating formation scenario involves primordial black holes. These hypothetical objects could have formed during the chaotic moments after the Big Bang, when fluctuations in the density of the universe may have created regions compact enough to collapse into black holes. Black holes come in different sizes and types. Stellar mass black holes are formed from dying stars and range from 10 to 20 times the mass of the Sun. Then there are supermassive black holes like Sagittarius A at the center of the Milky Way, with millions to billions of solar masses. These cosmic giants likely grew over billions of years, feeding on surrounding matter and merging with other black holes. Intermediate black holes are less well understood, acting as the missing link between these two extremes. They might form in dense star clusters where multiple stars collapse in quick succession, or through the merger of smaller black holes. While they are challenging to detect, their existence could help explain how supermassive black holes form. Finally, we have the intriguing possibility of primordial black holes. These hypothetical objects may have formed shortly after the Big Bang, when high-density fluctuations in the universe caused tiny regions of space to collapse under their gravity. Though they remain unconfirmed, primordial black holes could shed light on the nature of dark matter and the early universe. Each type of black hole represents a unique piece of the cosmic puzzle. From stellar remnants to ancient primordial giants, studying their diversity helps us unlock the mysteries of the universe's evolution and structure. Black holes have three main properties: mass, spin, and charge. Mass determines their size and gravitational pull. A black hole's mass can range from a few times the mass of our Sun to billions of solar masses, in the case of supermassive black holes found at the centers of galaxies. The mass directly affects the event horizon, the boundary beyond which nothing, not even light, can escape. The more massive the black hole, the larger its event horizon and the stronger its gravitational influence. Spin, or angular momentum, arises from the black hole's rotation. This property significantly impacts the surrounding spacetime, causing it to twist and warp. This phenomenon, known as frame dragging, can lead to the formation of accretion disks and relativistic jets. Rapidly spinning black holes, called Kerr black holes, exhibit even more complex interactions with their environment. Charge, although theoretically possible, a black hole's electric charge is generally negligible due to the equalization of charges in the universe. One of the most intriguing phenomena is Hawking radiation, predicted by Stephen Hawking in 1974. This radiation results from quantum effects near the event horizon, where particle-antiparticle pairs form. While one particle escapes, the other falls into the black hole, leading to a gradual loss of mass. Over immense timescales, this process could cause the black hole to evaporate entirely. This groundbreaking idea suggests a potential link between quantum mechanics and gravity, opening avenues for new physics. Black holes are not just cosmic anomalies but essential architects of the universe. Supermassive black holes anchor galaxies with their immense gravitational pull, stabilizing celestial structures and governing the orbits of stars and planets. Through powerful relativistic jets, they regulate star formation by expelling energy and matter, maintaining a delicate balance that prevents unchecked growth. Acting as natural laboratories, their extreme gravitational environments offer unparalleled opportunities to study high-energy physics and relativistic effects. Speculatively, black holes might even unlock gateways to other dimensions or reveal new insights into the fabric of space-time, highlighting their profound impact on both cosmic evolution and theoretical physics. Black holes stand at the intersection of two profound scientific theories: general relativity and quantum mechanics. Each offers insights into their nature but also exposes deep contradictions that challenge our understanding of the universe. Einstein's general relativity provides a framework for understanding how black holes warp spacetime, creating gravity wells so immense that nothing can escape their pull. This theory predicts the existence of singularities, regions of infinite density where conventional physics breaks down and space-time ceases to exist in its familiar form. Quantum mechanics, on the other hand, governs the behavior of particles on the smallest scales. Near a black hole's event horizon, quantum effects dominate, introducing complexities that general relativity cannot address. These two theories collide at the singularity, where neither provides a complete picture, underscoring the need for a unified theory of quantum gravity to bridge these gaps. One of the most debated puzzles involving black holes is the information paradox. According to quantum mechanics, information about matter cannot be destroyed. Yet, if black holes evaporate through Hawking radiation, as Stephen Hawking proposed, what happens to the information about the consumed matter? This paradox has inspired theories like the holographic principle, which suggests that all information is encoded on the event horizon, and quantum entanglement, which proposes connections between particles over vast distances. The study of black holes combines cutting-edge technology and innovative scientific methods to unveil their secrets. Among the most notable tools is the Event Horizon Telescope, EHT, a global network of observatories designed to capture high-resolution images of black holes. In 2019, the EHT achieved a historic milestone by imaging the shadow of M87*, offering a direct glimpse into the enigmatic nature of black holes. Gravitational wave observatories like LIGO and Virgo have revolutionized our understanding of black hole dynamics. These facilities detect ripples in spacetime produced by black hole mergers, providing invaluable insights into their mass, spin, and interaction patterns. Such observations open new avenues for studying these cosmic titans. Supercomputers play an essential role by simulating the complex physics of black holes. From the dynamics of accretion disks to the behavior of relativistic jets, these simulations allow scientists to explore phenomena that are otherwise impossible to observe directly. They act as virtual laboratories, deepening our grasp of black hole physics. Future missions promise even more groundbreaking discoveries. The Laser Interferometer Space Antenna, LISA, for example, aims to detect gravitational waves with unparalleled precision. These advancements will further illuminate the intricate workings of black holes and their influence on the cosmos, pushing the boundaries of our understanding to new frontiers. Black holes are not just cosmic mysteries, they're windows into the most extreme phenomena in the universe. From their mind-bending physics to their role in shaping galaxies, black holes continue to challenge our understanding of reality. Each discovery brings us closer to unlocking the secrets of the universe, but this is only the beginning. In the next video we'll explore what happens if you fall into a black hole. Spoiler, it's both terrifying and fascinating. So, stay curious, and join us on the next step of our cosmic journey.